Alice and Bob are playing a game where they start out with two arrays. One is a fixed array that will remain same across all the rounds, and one is a dynamic array from which players will take turns for deleting exactly one element in each round. But the rules of the game are different for Alice and Bob. In one round, Alice can pick any L, any index I from the fixed array. That is the first step. So suppose she picks index I and the value at this index is fixed of I. Then the next step is that she can now pick another element y from the dynamic array. Suppose the element that she has chosen is y over here. Then she is allowed to delete this element y from this dynamic array if y is divisible by the element that she had chosen from the fixed array. So that is why the constraints y modulo fixed I equal to 0. But for Bob, the rules are different. For Bob, he has to first of all pick an index I from the original array, from the fixed array, and then pick another element y from this dynamic array, and Bob can only delete this element y if this element y is not divisible by the element that was chosen from the fixed array. So you can see that in each round you have two independent choices that you can make from the fixed array as well as dynamic array, and removal is only possible if you make the choices that follow some constraints. And in any round, if a player runs out of moves, for example, after selecting any AI, they are not able to select a valid Y that respects the rules assigned to them, then they lose the entire game. So your goal is to figure out who will win the entire game, that is, who will always have a move available to them. And the constraints of this problem are that the array elements can be up to 10 to the power 6 for both the fixed array as well as the dynamic array. So this is the entire problem statement. Take a moment to pause this video and think about the solution before you move on to the future slides. Now let's discuss some strategy to solve this problem. So you will realize that this problem is a bit more complicated than usual number theory problems or game theory problems that you might have seen. The reason being is that you have two choices to make. It's not just starting with one array and then player taking turns removing elements from that array, just like what happens in NIM games. Because here you are allowed to make any choice in the fixed array, and then corresponding to that choice you are allowed to make some choices in the dynamic array. So how do we approach this? So we have to start thinking somewhere, even if that leads us nowhere. So of course the first choice that you might have is, what will happen if you fixed an index I in the fixed array, and then can you analyze which elements of the dynamic array can you remove and which elements of the dynamic array can you not remove. So suppose you fix this I, and then depending upon this fixed I, you can see that this dynamic array will now get partitioned into two disjoint parts. One part will contain all the elements which are divisible by fixed of I. So you can see that all these elements, they will have y modulo f of I is equal to 0, and the second half would contain y modulo f of I is not equal to 0. So this fixing an element AI partitions this dynamic array into two parts, and you can see that these two are disjoint, meaning Alice and Bob, they do not interact with each other, because Alice can only pick from this set and Bob can only pick from this set. So this set is reserved entirely for Bob and this set is reserved entirely for Alice. So this does give us some insight that if you fix AI, then you have some line of thoughts through which you can experiment. But it's not really enough, because yes, for a fixed I, it partitions this dynamic array into two parts, but then both of these are moving parts in the sense that these parts will change in each round, because this AI that you have just fixed, either Alice could have fixed this AI or Bob could have fixed this AI. So depending upon that, this thing might either rotate around, and the elements that are inside this box, those are also not fixed, because some of them might get removed in the upcoming rounds. So that is why this line of thought is not really leading us anywhere. Fixing AI is not really doing much. So then what is the alternate option that we have to think about this problem? To think about this problem from an alternate perspective, the only option remaining now is to fix a y and then think about how many choices are there for selecting the initial I from the fixed array, such that either Alice is capable of removing this y or Bob. So suppose I fix a y, then when can Alice remove this element from this dynamic array? So Alice can remove it if the ith element that you have chosen, that divides y. So Alice can remove it if y is divisible by the ith element that you have chosen. But you know that this fixed array will always be available to you. This is not changing for the entire duration of the round. This means that whatever elements you have available in the first round, you will have it available in all the future rounds as well. So you can say that y is divisible by at least one element in the fixed array, by at least one element from F. So in this case, you can see that Alice will be able to remove this element. When will Bob be able to remove this element? You can clearly see that if y is not divisible by at least one element, divisible by at least one element from F. From F, and if this condition is satisfied, then you can see that Bob will be able to delete this y. So you can see that since this at least keyword is appearing, then there might be scenarios where for a fixed y, Alice as well as Bob will be able to delete it. For example, if you have an element 8 as y is equal to 8, then if there exists a divisor of 8 such as 2 over here, then if Alice picks this 2, then Alice will be able to remove 8 from the dynamic array. But if 3 is also available over here, then Bob can as well pick 3 and then he will also be able to remove this y from the array. But whatever be the case, you can see that at least this line of reasoning only deals with the fixed elements in all the rounds. So with this line of reasoning, you can now split each y into three different classes. So let's see what those classes are. So in the previous slide, we talked about that y will be divisible by at least one element. So what is the complement of it? The complement is that if y is divisible by all the elements of fixed I, right? Let me write that down. So this is the fixed array, this is the dynamic array, and let me remove these constraints, and these are the rules of the game. So what are the possible cases? So the first case is y is divisible by all elements of fixed array, and the second case is y is not divisible by any element of the fixed array, and the third case is y is divisible by some and not divisible by others. So there are only three classes in which a particular y can fall into. Now, if you notice these three classes, that if y is divisible by all the elements of the fixed array, if this is y and this is divisible by all the elements of the fixed array, it means that Bob will never be able to touch this y at all, because no matter what index he chooses, this condition will never be true. Therefore, Alice can safely assume that all such y's will land into Alice's bucket. So let's color all such elements as green. All the elements that are divisible by all the elements of the fixed array, let's color it in green. And then what about cases where y is divisible by is not divisible by any element of the fixed array? So if y is not divisible by any element of the fixed array, then you can clearly see that Alice will never be able to remove this, because this condition will never be satisfied. So let's color all such elements in yellow. And then there are some elements for which they will be divisible by this and this, but not divisible by this or this. Then these are the ones where both Alice as well as Bob will be able to delete them in any of the round. Why am I saying in any of the round? Because this fixed array is fixed in all of the rounds. So that is why all the elements that land into this bucket, both Alice as well as Bob can remove it. Right? So this is both A and B. So let's color all of these elements in white. So once we have done all of these colorings, let's see what happens. So once you have done all of these colorings, then this entire array, all the elements of the dynamic array can be split into 3 buckets. So let's say you create all these buckets. One is the green bucket. You can already see that the ordering of all the elements in the dynamic array do not matter. So that's why I'm putting all the elements in the green bucket. And then there will be a yellow bucket. And then there will be a white bucket. There is this white bucket. Now you can see that this green bucket, this is entirely owned by Alice, because Bob can never touch any element of this green bucket. So Alice can be 100% sure that whenever she wants to, she can take an element from this green bucket. Similarly, this yellow bucket is purely controlled by Bob. So Bob can also be 100% sure that they can also retrieve an element from this bucket whenever they want. But this white bucket, both Alice and Bob are laying claims on it. So you can already see the optimal strategy, that if your goal is to maximize the number of rounds that you play in, and if these buckets are already written into your will, there is no rush to go and accumulate elements from this bucket, because they are there for you whenever you want. So your goal will be to grab as much from this bucket as possible while you still can. Otherwise, if you leave this bucket alone and if you start focusing on your own buckets first, then in this meantime, Bob can start collecting things from this bucket, and then he will have more rounds to play in. So we know that now the strategy is for Alice and Bob is very clear, which is find out how many elements are there in the white bucket and then finish the white bucket first and then finish your green bucket. And for Bob also the strategy is clear. First finish the white bucket first and then clear out your yellow bucket. So if I give you the count of all the elements in this bucket, can you tell me the winner of the game? So suppose the count in green bucket is G, count in yellow bucket is Y, and count in white bucket is W. So you can see that since Alice starts the game, then the first move that Alice would make is taking an element from the white bucket, right? And then Bob can also do the same. So Bob will just mirror the move, because Bob doesn't want to stay behind in collecting the elements from the common bucket. So Bob will just mirror the move. So you can already see that the only thing that matters for the W bucket is the parity, whether it is even or odd. So suppose it is of even parity. Suppose this is 4. So the first element will be taken by Alice, second element by Bob, third element by Alice, fourth element by Bob. And after the fourth element, the white bucket is completely over. And then it is Alice's turn again. So this means that this is equivalent to just playing the game on their individual buckets if the parity is even, because right now Alice is starting the game. But if the parity is odd, then still the strategy would be that Alice starts with the first element of the white bucket, Bob takes the second, Alice takes the third, Bob takes the fourth, Alice takes the fifth, and then there is no sixth bucket. So once Alice takes the fifth bucket, then the game is equivalent to being played on two separate buckets of green and yellow, and this time Bob will actually start the game. So now we have removed the white bucket from the picture altogether. So the only question is, if you are playing a game where you have G elements in your green bucket and you have Y elements in your yellow bucket, and if Alice starts the game, who wins? And if Bob starts the game, who wins? So you can already see that here the strategy is simple. Since you can only clear out one element from your bucket in each round, then whoever has the most number of elements will win. So if G is greater than Y and Alice is starting the game, then of course Alice will win. But if G is less than Y, then Bob will win. But the only thing is, if G is equal to Y, because if G is equal to Y, then you can see that if Alice is starting the game and both of them have 5 elements in their buckets each, then every time Alice does a move, Bob can mirror the same. So 1 1 and then 2 2, 3 3, 4 4, 5 5, and then Alice will be the first one to run out of moves if Alice started the game. But if Bob started the game, then then Alice can mirror the moves and then Bob will run out of moves. So in this manner, you can solve the entire problem. So just to recap once again, if you can somehow find the count of elements in the green bucket, find the counts of elements in the yellow bucket, and find the count of elements in the white bucket, then the strategy is to pick all the elements from the white bucket as quickly as possible by alternating turns and basically by mirroring whatever your opponent does. And then once the last element is gone from the white bucket, you will play your independent separate game on your green and yellow buckets. And depending upon the parity of the white bucket, you have to decide who will start this simplified version of this game. And whoever starts, the other person can just mirror them. So whoever has the more number of elements in their bucket, they will of course win. And the only corner case is when you have a tie. So when you have a tie, then you of course have that mirroring strategy, and that mirroring strategy will depend upon what was the parity of the white bucket. So now you have solved the problem. The only part remaining is how to figure out the number of elements in the green bucket, how to figure out the number of elements in the white bucket and the yellow bucket. And this is where the game theory part of the video ends and the number theory part of the video starts. And you view this number theory part in isolation, because these game theory concepts that we have studied so far, like mirroring a strategy and trying to take things from the common pool first instead of going for your own bucket first, these you can reapply in future game theory problems. But the next part that we'll discuss, those are specifically related to number theory, and those you can only apply to future number theory problems. So now the problem statement is this, that you are given two arrays. One is a fixed array and one is a dynamic array. But now it does not matter, because for each element, our problem statement is this. For each element y in the dynamic array, find out how many elements are divisible by it. If that number is n, which is n is equal to the length of the fixed array, then this will fall into the green bucket. If that number is 0, then it will fall into the yellow bucket, right? And if the number is anyway strictly greater than 0 or and strictly less than n, then it will fall in the white bucket. So all we have to do is, problem statement is, let me write that down. So the problem statement basically says, for each y, find the number of divisors of y in the fixed array. This is the simple problem statement that we have to solve. Now let's see some approaches to solve this problem. First of all, since each element in the fixed array is in the range 0 to 10 to the power 6, or let's assume it's 1 to 10 to the power 6. 10 to the power 6. Then you can convert this entire fixed array into a frequency array, where for each element you maintain how many times the element occurs. Because of course the ordering does not matter in this problem. So you maintain the frequency. For each element you maintain the frequency array. Then for a fixed element y, how many elements can divide it from this fixed array? So of course those elements have to be one of these numbers from 10 to the power 6 with greater than 0 frequency. But what are the elements that can divide a particular number? Those are nothing but its divisor by definition. So the problem is now, how do you find out all the divisors of y? And for that you have a square root algorithm that works in square root of n, basically this root of n, wherein you say that you do a brute force and you check all the divisors up to n. So this will be O of n, but the divisors have a very interesting properties, that if d is a divisor, then n by d would be an integer, and if n by d is an integer, then n by d also divides n, because n by d is equal to d. So you can see that if d is a divisor, then n by d is also a divisor. This means that it will partition this. If you have a number line, if this is root n, then you can see that any divisor on the left hand side has a mirror image on the right hand side, because if this is d, then this is n by d, and both of them are divisors. And this is in fact the complete set, because if there was indeed one divisor that was on the right hand side, then it must definitely have a mirror image on the left hand side. So if you just iterate to root n, then you would have iterated over all the divisors. And why is this root n coming into picture? Because the mirror images become equal at this point. D is equal to n by d, so d square is equal to n, so d is equal to root n. So therefore, for a given number n, if you want to find out the number of all the divisors, then you just have to iterate from left to right up till root n, and every time you find a divisor d, you also kind of implicitly assume that there is a divisor called n by d. So the time complexity of this is root n. So the strategy for this is simple. You iterate over this dynamic array from left to right, and for each element y, you do the square root factorization and find out all the divisors. So each element will take root n time to do the factorization, and then you can do the lookup. For each divisor, you can do the lookup how many times is it present in this array. So the overall time complexity becomes n root n, which is not bad, which is of course better than O of n square. But can we improve upon it? Can we do it in O of n log n? So this is the final stretch of the problem, that we are trying to solve a number theory problem, which is asking us to find the number of divisors of an element y from this fixed array in a faster time. So let's see. How do we find out this? So the idea is essentially the same as the game theory one. So in the game theory one, you will remember that we tried two approaches. One of them worked out for us, one of them didn't. The first approach was, what if you fixed I and then you tried to reason about the elements from the dynamic array. So you saw that it was difficult to reason about because the elements in the dynamic array, they were changing a lot. So then you flipped the perspective and then you fixed an element from the dynamic array, and then you tried to reason about the elements in the fixed array. So can we apply that same trick here? Yes, you can. So instead of fixing an element y and then worrying about all its divisors, why don't you fix an element f of I over here and then worry about how many elements are multiples of it, because the reverse of a divisor is a multiple. So if y modulo f of I is equal to 0, how do you read this statement? First of all, there are multiple ways to read this statement. This means that f of I divides y. That is one interpretation. Second interpretation is that f of I is a divisor of y. Third interpretation is that y is a multiple of f of I. So this is the most important interpretation. So it's just a different way of looking at things. So y is a multiple of f of I. So if you go by this line of reasoning, you can see that if you instead started out with f of I, this is f of I, then for each f of I, you can iterate over all of the multiples of f of I in the dynamic array and then increment their counter by 1, because in the reverse lookup, this element y will have to look up this f of I. So why not do it in the other way around? So let's not worry about the time complexity first. Let's focus on the correctness. So if you do it for each f of I, then you can see that each multiple, so each f of I will increment the count of all of its multiples. So suppose this is 2 into f of I and this is 5 into f of I. So every time you encounter f of I, you increment the count of the divisors of these elements by 1. So at the end, you can see that this particular process is exhaustive. This means that it has covered all the possibilities. Because why? Because there is a bijection. Because if f of I is the divisor of y, then it means that y has to be a multiple of f of I. So due to this bijection, if you iterate over all the multiples of f of I, that is as good as iterating over all the divisors of an element y. So the algorithm would be, final algorithm would be, for I in 1 to 10 to the power 6, like you have maintained the frequency array, right? And now you want to iterate over all the multiples. But how do multiples look like? So the multiples would look like something like this. So multiples are simply I, 2I, 3I, 4I, 5I, and so on. So you can simply say that for j in 1 to 10 to the power 6, and then you simply increment the count. You do count of, you are multiplying I by j, right? So you are just doing count of I into j plus equals to whatever the frequency of I is, right? Plus equal to frequency of I. So the time complexity right now that you see on the screen, that will come out to be O of 10 to the power 12. Now let's see if we can tune these limits even further. So you can see that this j is the factor, right? J is the multiplication factor. So you don't really need to vary it till 10 to the power 6. You can write this condition like so. You can add an early break, like say and j, and then you can add a condition like so, and because the number that you are incrementing, it has to exist in the dynamic array, and that number is I into j. So you can say I into j is less than or equal to 10 to the power 6. So with this extra condition, like just adding this additional condition, we claim that the time complexity has now come from 10 to the power 12 down to simply 10 to the power 6 into log 10 to the power 6. Now it might sound very fancy, but let's see how this is actually working. So let's go step by step. For 1, like if you have a number line 1, 2, 3, and this is up to n. For an element 1, how many multiples will exist in this? And here n is equal to 10 to the power 6. So how many elements will you mark as a multiple? So you can see that all the elements are multiples of 1s, right? So how many elements? There are n elements. But for 2, how many elements will you mark as multiple? So you can only mark in jumps of 2, right? So there will be only 2 elements. So you will only traverse this second loop n by 2 times in this for I is equal to 2 case. But for 3, you will see that you will only mark elements in the jumps of 3. So this is 3. So you will only traverse that second loop n by 3 times. Same for 4 as well. So this final sum comes out to be n plus n by 2. So these many operations you are doing, n by 3 plus n by 4 plus n by 5 plus n by n. Why? Because for the last element n, there is only one multiple within that range. So this is nothing but n into summation of 1 by I, which you will know that by harmonic series, this is log n. So the overall time complexity becomes n log n. So now we have a strategy to compute the number of divisors for each element y from the original fixed array in O of n log n. And once we have this, we can apply our game theory strategy to solve the original problem. So you can see that this problem just took some concept from number theory, just took some concept from game theory and concatenated them. There is no like interleaving between them as such. And this is in fact a good problem for you to understand how that mirroring strategy and how to think about game theory problems etc works, because when we started this problem there were so many moving parts that we didn't really know what to do. But once we started to flip our perspective, that is fix I and then think about this, didn't really help, but fix this and then think about this, it started helping. So this was in game theory, but for number theory we saw that fixing this and then started worrying about this didn't really help, but fixing this and then started worrying about all the elements here via multiples, that helped a lot. So in competitive programming problems you will find this idea a lot, where you fix one thing and then you try to vary the other thing. It might not lead you anywhere, but if you flip your perspective and think from a different angle, think creative, think outside the box, that will help you simplify the problem. And yeah, it will help you solve a lot of problems. So that is it for the video. And let me know if you want to solve this problem. I'll link it in the comment section. Otherwise, even if you don't want to, that's fine, as long as you have understood the idea. Thank you.